All right, so this is the third module of Lecture 17, Naive Bayes Classifier for text classification. So this, I'm going to reuse some of my last year's recording, and this module is required for my master level, but not required for the undergrad level. All right, so what I'm going to talk about is how do you learn the parameters of a multinomial naive Bayes classifier on the text input, and how do you use the model to perform classification on text input in this module. Okay.
Okay, so now I'm going to talk about multinomial naive Bayes classifier. So I hope you still remember what is multinomial from your probability class. So in the end, what we're trying to get is this joint conditional probability. So all this vector of counts, what is the probability given a specific class? So in this case, words are like a colored balls, right? There are k possible color balls. In this case, actually, it's the vocabulary size. And in total, so for a document contains n words, a capital N words. Each word occurs ni times, like a bag of n colored balls, right? How do you represent its probability? Very classic representation of probability function to model this type of count vector is the multinomial distribution. So before I talk about multinomial, let's cover binomial, because we understand Bernoulli, and then Bernoulli is really just let's see. So the binomial distribution is a count of the success of events over n. So if you flip a coin, you flip n times, and the distribution of how many times the heads appeared is a binomial distribution. So not to get you confused, we just covered you HH or TH onto maybe H. You just flipped, you actually flip the coin for n times. And the number of times is the head. This is a random variable. Actually, this is the random variable. This number of times a head appeared is a random variable. This random variable is its distribution is the binomial distribution. Don't get confused with the Bernoulli. Bernoulli will only represent the probability for a single flip the coin. Is it a head or is it a tail? And here we care how many times head appeared over n flipping coins. It may only appear like maybe one time, two times, until n times. So all the possible numbers of this random variable. Let's just treat this random variable as x. X is the number of times had appeared through n times of flipping the coins. X, what are the event space? Let's remember, whenever there's a random variable, you need to understand event space or elementary event of a random variable, right? What is the elementary event of this random variable x? 0 to n. Yeah. So for the Bernoulli variable, what's the elementary event for the Bernoulli variable? Head and tail. So try to be clear about the differences of both. So Bernoulli, it's about counts. Okay? And when you're trying to figure out what the Bernoulli distribution is, you actually have the two parameters. First is actually that n, so how many times you flip the coin. And the second is the p. So for each flip the coin, what's the probability it's a head or it's a tail? So, and n head plus n tail equals to n, and the p head and p tail summation equals to 1, right? This is binomial distribution. Then you just extend this into multinomial distribution by allowing not just 2 events, but actually allowing k events. In this case, like roll the dice is 6 events. In our case, the dictionary, our dictionary is much larger, and you're calculating each possible elementary event, it's a number of occurrence. And this is what you're observing. And the multinomial representing this joint vector representation, joint vector probability. Of course, it needs to satisfy if the first appear n1 times, if the second elementary event appear n2 times, n1 plus n2 until nk equals to n, because that's the whole number of times this you perform the throw of the dice or the flip of the coin. And also the probability, so the parameter of multinomial distribution is this total number of n, and also the likelihood, the probability of each elementary event appears. So in this case, it's theta 1 until theta k, and theta 1 times the summation of theta 1, theta 2 until theta k is 1. And the parameter in the end, in this case, is this theta 1 to k vector, probability of each elementary event, how likely they appear, and the parameter of number of times you observe that event. Okay, and then how do you write this joint probability, which is super easy, right? I mean, we actually always remember that because the first elementary event, the probability is theta 1 condition C, and I observed it n1 times. Of course, it's just n1 to the power of n1, right? A theta 1 to the power of n1. Then the second event, second elementary event, is theta 2 to the power n2 until the theta k to the power of nk. And I hope you remember this term because so anyway, this is the possible ordering and the factorial over all the other factorial because we don't care about the ordering. Anyway, so however, in our case, because this term is, so what do we observe or try to estimate from data? If I want to estimate this multinomial distribution from the data, what is unknown? So I already said, right, for multinomial distribution, what you need to know is first is the whole number of times you observe the event, right? And the second is theta 1, theta 2, until theta k, right? So then condition on the C. And this is actually the model you need to observe. So let's assume this is called theta n. For each document DI, you actually know the n. You know the full length, right? That means this is the number of times those color balls on this word article appeared. How do you see the different words appeared, and they appeared n times in total. And you actually know this n. You don't need to estimate it. It exists for every document. And then, but you actually do not know theta 1 until theta k, condition on the C, right? You need to estimate this from data. So when you're doing argmax, and what matters, this n is actually the same for every article. When you perform for a specific article, the n is shared, and n1 and 2, they're all observed. So that's why you don't even need to do this, perform argmax, because for different classes, this parameter is shared. So in the end, this portion is not related to C. That's why we don't need to use it. That portion is not relevant to a specific class at all. And the only thing you compare is this quantity. Question about this. And this is how you get the joint probability, right? The joint probability is this scalar because it's not relevant to C. And when we're performing classification, what we do is argmax, right? It's argmax over C, E, W1 equals to N, N1 into WK equals to NK, condition specific C, and then times PC. And you just substitute this thing into here, and because you're doing argmax over C, and this quantity is not relevant to the C at all. So that's why this is the one you use to perform classification. This actually saves a lot of calculation. Yeah, because they are labeled invariant. And then the model you need to estimate in the end from the data is theta1 onto theta k, condition on C1 onto CL, and this is the matrix you need to estimate. This is your model. The multinomial model you need to learn from the data. Question about this? All right. So yeah, this is exactly trying to show you the testing rules. So what MAP formulation you're using to get max C, and this is the rule you're going to use. This is the testing stage, which is the one you're going to implement. Of course, what you should implement is the log version of this, right? Right, so now let's see, how do you estimate those from the training data? So I want to estimate this matrix from data, from my training data, and this is a K times L number of parameters, right? So same thing. So how do you estimate multinomial distribution? Assuming, so just to simplify, this is no condition on C for now. So there's no condition on C, just from the data, how do you estimate multinomial distribution? Maximum likelihood estimation. You just substitute this and D, it's really just that W, right? Each specific document is the word first is equals to N1 for the document T. W2 is N2 in the document T onto WK in the document T. Right? This is that's actually D in the representation. And then you just use the multinomial representation. You substitute here for each document represented as a multinomial joint probability. And then again, this is even not relevant to the theta. It's not relevant to theta. You perform your argmax, you just cancel this out. And then this is the one you maximize over all the documents. Subject to summation theta1, theta2 onto theta k equals to 1. Okay, so how do you maximize that? You have theta1, theta2 onto theta k, k different parameters, and you have one loss function. So this is a little bit hard. I'm not going to cover that. There's an extra document. It's actually not very difficult too, because you can decompose this to be only just related to each of the theta, and because this is called a constraint optimization, which we covered a little bit in the SVM formulation. It's actually not hard at all. Is to add this part into the loss formulation through a Lagrangian multiplier. You're just trying to maximize things together. You take gradient, set it to 0, and you're going to get the theta I for a specific elementary event. For a specific elementary event, the MLE solution is, so over all the samples, in our case, over all the documents, the summation, the number of total counts that specific elementary event, that specific word appeared, over the summation of every sample. So this actually means this is the whole length, how many times, it's really just the length of your whole training data. And so assuming this is actually not considered the class label yet, right? Just when given that data, you try to estimate a multinomial distribution. There are multiple text samples, and this is the full number of word counts of that data. And this is the number of word counts of that specific word. And this means what? To perform multinomial distribution is actually extremely easy. So again, just to clarify the context, we're not conditioned on the C yet. We're just giving you your data. How do you estimate multinomial distribution? I'm giving you multiple text samples and a dictionary of W words, right? W1 to WK words. Very easy. You don't even need to care those different samples. You put all the samples together, put all those samples together, create a mega document, and then you just, upper is how many times this word appears in this mega document. The length of the mega document is the probability of theta I for that elementary WI. So so I'm trying to repeat it. We can create a mega document by concatenating all the documents D1 to DT, and then we use a relative frequency of specific W, a specific elementary event, and then this gives you the multinomial specific theta for that specific W. Okay, question about this? It's hard to ask a question unless you perform this the MLE solution, but feel free to do it by yourself. And this takes a little bit more time. All right, so now let's see. We use multinomial distribution in when we have a C variable, which is, so I should actually write C. So what I'm conditioned on, I should have theta 1 and C. Yeah, so this is D1 to your training data. I'm trying to estimate this matrix. And this matrix is, again, W1 to WK times C1 to CL. And how would you do that? So you just, for each class C labels, you create a mega document. For each class C labels, you create a mega document, and then you just, you count how many times the W appears in each mega document, and that's how you get P. That's how you get P W specific I for a specific CJ. It's a very easy solution. It sounds very complicated from a multinomial perspective, but in fact, its training and testing is truly simple. Yeah, question about this? There's a little bit. Yeah, this means the WI, specific WI words, and this gives you the theta WI and CJ. All right, so yeah, just kind of repeat it for a specific C, and you just yeah. So yeah, I think this is more concrete. You can read it when you implement the algorithm. This is just more like a flow representation of how you implement training. Okay, just to summarize, naive Bayes model is actually not very naive at all. It's a very solid baseline for text classification. It's very robust to the irrelevant features. It's also very good to, it's a very good approach when you have many equivalent important features. And it's a good solid baseline, and it's optimal if the assumption holds. And the other big reason is it's super fast. It's actually super fast. So think about how do you implement this? Okay, let's go back to this algorithm. How would you implement to get this matrix? It's actually super fast. You only need to go once. One pass of all the training data, you can actually get this. So for class, you know the class label, right? You just concatenate whoever being classified as C1, create a mega document, and then you loop over each word through that mega document. If it's a hashing, right? If in the W1, W1 got class 1 count. If it's W2, W2 got class 1 count, right? Think about this. For the C1, you got a mega document. It's you create a hashing. You just remember, keep just class 1 when you meet W1 or maybe WK, whatever. Just one pass of the C1 document. You got that column vector. Then you do the C2, C onto CL. And this actually means only one pass of all the data. And the cost is, so assume you have T documents, the average length is TD, the cost is only T times LD. And yeah. Oh, I see. I think you need to normalize it, right? Yeah, there's another cost. Okay, so this is the handling the training data cost, right? You touch each word, doing this sweeping operation over all the documents, and then you got that matrix. So after that matrix, and then you need to do normalization, right? That normalization touches every entry of that matrix, and the size of that matrix is C times V. It's the number of words times the number of class. And this is super small, actually, TLD plus CV. And the test time is actually pretty quick. So you're really just for, so that's a matrix model, right? W1, W2 until WK or V, which is the same thing. C1 until CL. So when you perform test, it's actually the same thing, right? You need to convert your testing data into this vector form, but you don't need to do backwards representation at all. You only need to count. Yes, actually that's true. So in let me see. This is in the testing stage. So let me ask you. Yeah, this is the testing stage. How do you implement this testing stage? How do you implement it quickly? So there's one way. There are two different ways, right? The first way, when you are given a document, it's a document just a sample. It may be like double I words and double J words or whatever. It's not a backward words representation. Let's start from there. until the length, maybe represent length, maybe that's specific L. So how do you represent this testing calculation? So there's two ways, right? The first way is you convert it into backward words. The second way actually is what? Don't even bother. For each class C, I do PC. If I meet the first word, I'm calculating that specific first word's probability. And then I move to the second word. I'm just times that second word's probability. I don't even need to have the backward representation. It's just PC times P first word I met, the position, P word, the third word I met, P2, until the last word I met, P, maybe L specific D. And this is actually equivalent to this. And this is a homework. Yeah, it's actually very easy to derive this. And this computation of this is actually faster than this. And you can derive it very easily. How do you perform backward words? And using this versus no backward word at all, you really just loop over all the words, then using the parameter you estimated and one pass. And this is all the length of, that's exactly what we showed in here. The cost of testing is C times the length of the document. All right.
Great. So this is the end of this module. See you in next module.